Thank you, Maria. So for the next 2 hours or so, we're going to go over post-tension concrete construction and observation issues. I give several webinars for SK Ghosh and Associates, and I think this is by far my favorite one, primarily because there's no numbers involved. It's, as George Bush would say, it's the shock and awe approach. It's just the train wrecks and here's what could happen if you don't do it correctly kind of thing. So no engineering, no code sections for the most part. I don't think there's any calculations, but it's just a lot of, look out for this, because if you don't, this is what could happen. Obviously, as Maria said, if you have any questions about any aspect of it, please type them up and I will get to them the best I can between the breaks. And also my email address is listed on the bottom of the first slide and the last one as well. So if you have another question or something comes up, please send me an email. I'll do my best to get back to you as soon as I can. The webinar topics we're going to go out today are tendon layout, look at curving of tendons, anchorage zones, pour strip and delay strips, which are common in post-tension concrete for stressing, also for subterranean projects, because obviously you can't stress outside the building. But there's a lot of intricacies besides just the straight numerics. We'll go over slip connections, penetrations, integrity tendons, which is a very specific code requirement. And it's one of those code requirements that is prescriptive. There is no numerical way out of it. But there's actually a very, very important reason it's there, and I'll cover that as we get there. Now, if any of this is interesting at all after you hear the webinar, my business partner, Dirk Bondi, and I wrote a book during the last recession and have updated it 4 times, actually. And this covers all aspects of post-tension concrete relative to building construction, of course. The first part of the book is the undergraduate post-tension course that Dirk teaches at a couple universities, primarily in California, UCLA and Cal Poly San Luis Obispo, but it's also used elsewhere. The second half of the book is basically what we do in the practice or the business side of post-tensioning, how to design foundations, how to design plates, garages, podiums, stuff like that. So there's a lot of pictures in there, a lot of do this, don't do that kind of things from our experience. And like I said, it's a lot of pictures, a lot of graphs, a lot of details. So it's an academic side of things, but there's also a practical side to the second half of the book, which will hopefully make it useful for students as well as more seasoned or practicing engineers. Now, in general, when we talk about post-tensioning in building construction, especially in North America, we talk about unbonded post-tensioning strands, which you can see in each direction on this particular photograph. This here is a two-way flat plate, so you have the bands in the very top portion going left to right, and the uniform tendons obviously going up and down the page at 2 or 2.5 feet on center. As I mentioned before, we're all talking about unbonded strands, meaning the strands are sheathed and greased, so there actually is no bond, there is no string compatibility, between the concrete and the post-tensioning. They're completely slipped. The only quote-unquote interaction is you get from the anchors of the concrete pressing into, or the anchors when they're stressed, pressing into the concrete, and that pre-compression force emanating throughout the slab, and that's your P over A aspect of post-tensioning. But the one thing about doing observations, especially if you're a new to post-tensioning, is everything in PT should be very gradual, whether it's the vertical movement of the PT, which is what we use for balance loads and to minimize stresses and control strength, to curving strands horizontally to avoid penetrations or to connect to a column or whatever reason. Everything should be done gradual. When I do observations, I take a much more of a global approach. I don't recommend counting strands or counting rebar. It's more or less look for the oddities, look for the kinks in the strands, whether it's a vertical kink, which can cause localized uplift forces or blowouts, or it's a lateral kink, which can create a lateral force in the slab, which can usually cause cracking and blowouts as well, which I'll cover in a little bit. So basically, the general concept is always to have uniform spaced, gradual profiles vertically and horizontally, which you can see here. Now, in the opposite direction of a two-way flat plate, you have the banded strands. Now, I'm not going to get into the difference between a banded and a uniform in the numerical sense. It's purely a construction issue. You design the slab the same way in both directions, but you group them differently in one side versus the perpendicular direction solely for constructability. So basically the same aspect applies. You're wanting to have a profile of the strands that are gradual, that hit the high points over the supports, meaning the columns, the walls, or the beams, and then a low point basically at mid-span to match your moment diagram and to match your design calculations. The one thing, again, I try to look for is not so much did they exactly get 1¼ inches from the bottom of the forms or 7¼ inches at the columns. That's the inspector's job, and they usually do a very good job of making sure your design is implemented. What we try to do as an observation issue is more of the global inspection, not so much the minutia, is make sure they don't have kinks in the strands. And if you can look here, I realize it's a little hard to see, but if you were to look right here, you can see the strands are coming down, and then there's a whoop-de-doo right there in the system.